Okay, so good morning everyone, and thank you for being here. And I'm Mathias, I'm a postdoc at Thiago Quental's lab in São Paulo University. And I'm going to talk about a project I've been developing with the help of Daniele and with Thiago. And it's about the radiation of Carnivora after Cenozoic continental faunal exchanges. So, when we think of species colonizing a new environment, what we see, or what we might expect to see, is that lineages may undergo an evolutionary radiation after colonizing a new environment, and what characterizes these evolutionary radiations are fast species accumulation, right? So, and sometimes we are also interested in the increasing morphological disparity or ecological diversity, which we call adaptive radiation, but here we'll focus on the richness, on the diversity of species, okay? So most of the examples of insular evolutionary radiations come from insular environments, and what we see several times that there is radiation after colonization events. So some examples are the Anole in the Caribbean islands and the Malagasy fungid. And so we have the theory tries to explain these evolutionary radiations in terms of ecological opportunity. So in an island, we expect to find lower diversity, and which means species will face less biotic interactions, and these might lead to a release for network selection, which might lead to ecological release, and by some unknown ways, these might lead to unconstrained diversification and finally adaptive radiation or evolutionary radiation. And these patterns, these macroevolutionary phenomena, which are bursts in diversification, they might be easier to detect in islands, but we do have a few examples at the continental scale. So one example is the rat snakes, which after invading North America seem to have underwent an evolutionary radiation, with many species arising from after this colonization process. And another example are myrid rodents, which after invading South America diversified in lots of different species. And possibly the explanation for these two radiations at the continental scale is that these groups they had no ecological analogs in the continent they migrated to. So these are a few examples of that showing that we might have radiations at the continental scale as well. But these were not the only events of migration that may have resulted in radiations. So we know that faunal exchanges were frequent, and one example that we have is are the exchanges between North America and Eurasia, which were connected during most of the Cenozoic. And we still don't know what were the microevolutionary consequences of these exchange events, of many of these exchange events. So that's what our main question was, and we had our working hypothesis that maybe immigrant lineages should undergo radiation because they would find less ecologically similar species in the new continent, in the continent that they're invading, than in their continent of origin. And the predictions that are related to these hypotheses that we should find high speciation of a lineage after invading a new continent or a new region, and this speciation should drop after this initial burst, right? So to study and to test this hypothesis, we analyzed the macroevolutionary rates of 8 families within Carnivora, and we used data from PBDB and now database, and after extensive process of trying to deal with the taxonomic problems of these groups, and then we obtained the maximum and minimum age for each occurrence of each species in each of those families in each continent, so in Eurasia and North America separately. And we used Pires, which was developed by Daniele Silvestro and colleagues, which is a hierarchical Bayesian approach which jointly estimates times of speciation and extinction, preservation rates, root age, and rates of speciation, extinction, diversification, and the shifts in those rates through time. So here, now I'm going to show some results, and these graphs, they show the root age, the posteriors of the root age for each family in each continent. So in this yellowish color, we have a brownish color, we have the posteriors for the clades in Eurasia, and in bluish and or greenish, we have the posteriors for the clades in North America. And we can see that these clades at the left, they most likely first appeared in Eurasia and went to North America. And these clades, they most likely appeared in North America first and then migrated to Eurasia. Okay, so now let's look at the speciation rates through time. So here we have in this color, we have here we are considering only the species in Eurasia, and here only the species in North America, and these are the same colors that I'll use for the rest of the presentation. So now let's look only at the lineages that went, the families that went from North America to Eurasia. And what we can see here, I'll highlight for you because it's easier that way. So we can see early peaks in speciation rates for these groups that went from North America to Eurasia. Whereas we can see these early peaks or any peaks is more uniform in North America. And when we look at to the families that went the other way around, from Eurasia to North America, what we find are more uniform dynamics or flat, these flat speciation rates through time. Okay, so. And there are also some interesting patterns that we find when we look at the extinction rates. So, looking here at the lineages that went from North America to Eurasia, we can see that besides the highest or initial high speciation rates, we can also see high early extinction rates, at least in these three groups, right? Amphicyonidae, Eurasia, and Canidae, but not in Mistretta in this case. And another interesting pattern that emerged from this analysis that we can see that here in the boundary between the Miocene and the Pliocene, we can see that most lineages, especially in Eurasia, they underwent an increase in extinction rates as well. So we can see these here. Okay. I think I'm going too fast. Sorry. Okay, so. The bottom line, I think the main result that we got from these analyses is that only families invading Eurasia show early peaks in diversification. And the best way to see that is looking at diversification rate plot. So here we only have the median for you to see. So, but we can see these bursts in diversification in all the clades that went from North America to Eurasia, and not on the lineages that went the other way around. But, so the question that we asked ourselves is, why do we find such an asymmetric pattern, right? And we try to explain this in terms of differences in ecological opportunity between the continents. So, what we see here is that Amphicyonidae, Eurasia, and Mustelidae, they radiate almost at the same time in North America. Here in the boundary between the Oligocene and Miocene, we can see these bursts. Whereas Canidae is a different story, but I'll tell you later. So they radiated a bit later. So what was happening at this time in Eurasia is that we had a very low diversity of carnivores at this time. And Creodonta, which is a carnivore but not a carnivora group, and they were the main carnivores in Eurasia. At that time, they were already declining at this time. So the decline of Creodonta, well, at least this is what we thought as a hypothesis to explain these results, that the decline of Creodonta might have presented the ecological opportunities for the radiation of these groups that enter, and there were no carnivores there, almost no carnivores there, right? And Canidae is a different story because they invade Eurasia much later, here in the between the Miocene and Pliocene, and they diversify. At the same time, other carnivores are declining, which is interesting. We can see here that there are many clades in decline here, and Carnivora has this high diversification rate at this point. So we thought these extinctions might be giving the canid the opportunity to radiate. And also at this point in time in Eurasia, we saw the expansion of grasslands. So maybe some kind of conjunction between these, the extinction events at this time and the expansion of grasslands, they might have bolstered presented the ecological opportunity for canid radiation in Eurasia. What happened in North America, where we don't see any carnivore radiation, is that in North America, Canidae is the only family that underwent an early radiation, but very early in the boundary between the Eocene and the Oligocene. And what we thought might have happened is that Canidae may have prevented other families to establish and radiate because they radiate very early. So maybe the radiation of Canidae somehow had some barrier, presented a barrier for the other families to radiate. So, well, these are the conclusions then. We thought that we found that the asymmetry in the macroevolutionary consequences of exchange, they may represent an asymmetry in ecological opportunity between continents, and that radiations may include both high speciation and extinction, as we saw for some groups. And this is a pattern that is hard to grasp without fossil data. And we also saw that radiations may be important in shaping diversity patterns at the scale of continents, and not only in insular environments or lakes. And so I'd like to thank all my colleagues in the lab and evolution meeting, and Daniel Silvestro and FAPESP, which pays me for everything. And that's it. Thank you.
So you're talking about the spread of grasslands in Eurasia.
Yes.
That's very interesting. So how would you link, I'm saying ecologically speaking, the spread of grasslands with the radiation of canids? Like, would it be, I don't know, I'm just wondering, but maybe food resource?
Yeah. So one interesting thing that happened is that Canidae had 3 subfamilies in North America, well, at least along the Cenozoic, and only one of these subfamilies were able to reach and radiate in Eurasia, which is Canidae. And most of the Canidae, they are somehow adapted to a pastoral life, and they are used to, most of them are related to grasslands and open habitats. So maybe that's the function of an ecological relationship between grassland, the expansion of grasslands and canids.
Well, yes.
Yeah. What about the environmental setting of those different regions at that particular times? Have you thought about that? If that was climatic change at that exact time, or the same climates from one region and then the other, so that it's easier for those particular canids to radiate? Because they already have not only the ecological adaptation at the local scale, but also the environmental scale.
Yeah. So interestingly, these 2 points in time, the Eocene-Oligocene boundary is when we have the main cooling event from the greenhouse to the icehouse cooling, and that place between the Miocene and that time between the Miocene and Pliocene is exactly when we have the Messinian crisis in Eurasia, which was the event that is characterized by higher temperatures and lower rainfall. So maybe this is probably playing an important role there, like allowing species to migrate and allowing them to establish and lineages to establish, and also, yeah, probably there's an important role.
Yeah, I like your talk, and I like that you're focusing on these continental radiations, and I like the contrast that you drew with the adaptive radiation theory, which is focused on these more local, geographically local radiations. And so, I guess thinking about the signature of diversification, whether we want to call that an adaptive radiation that is similar to what we see in anoles or cichlids or what have you, or if we should be, what you're picking up is diversification of speciation, species accumulation that will probably include, if your ecological opportunity hypothesis is correct, is adaptation to divergent niches, but also there's more range at these for these continental radiations, right? So there's a geographic component that is not sort of explicitly articulated in these ecological adaptive radiation hypotheses. And you know, thinking in terms of how to move our conceptual framework for macroevolution forward, you know, it seems like disentangling the geographic component or explaining what the geographic component versus the ecological opportunity component would be important. Do you have any comments on that diatribe?
Yeah, so one of the things we know is that Eurasia is bigger than North America, and it might contain more bioclimatic regions and things like that, and probably these somehow is somehow related and had some impact at the diversification of these groups when they got there. Well, they have more places to go when they get to Eurasia, but that's a very hard thing that we can get with the fossil data because they're not uniformly distributed, especially in Eurasia. So we raised this possibility in the manuscript and all, but we don't know actually how to test the relative effects of like one plate being there or incumbent lineages versus the fact that Eurasia is bigger and may contain different habitats. So.
We'll have to stop here. I'm sorry. Just thank you and thank you for the speaker.